So example 3 on page 547. So it looks like this one has like TNT versus the magnitude of the explosion it could cause. So let's see. So we have a data set. Which one of those do you guys think is like the variable that's explaining the other one? Which one's the x variable, the independent variable? I think it's TNT, yeah. So x, we'll say TNT, and that's in tons. And the way they have it in the chart is a little bit crazy, so let's see if we can figure out what they mean. What else? Why? Magnitude of the explosion. What are they measuring that in? They give us units?
Just on the Richter scale.
Okay, so this is like the magnitude of like an equivalent earthquake on the Richter scale, because the Richter scale kind of measures like seismic events, and an explosion could cause that kind of thing, or an earthquake could cause that kind of thing. Okay, so I think the magnitude ones are easy. We got 2, 3, 4, 5. What are the numbers of those other ones? They chose to display it weird, I thought. First one is 1 ton of TNT. That's not 1 stick of dynamite, that's a ton. That's a lot.
So is the next one 30 or is it?
I'm not sure. I think they mean 30. You guys see they have like 3 tens, so I'm thinking they mean 30. So then the next one, they say 1,000 tons. They're weird though, like they put these in a box. Is 1,000 tons of something gonna fit in a box? It's really weird. And what's the last one?
30,000.
30,000. Okay, so I think that's the data we're supposed to model. So let's just put it in our calculator and look at it. Now, I want you guys to look at this. X versus Y. Remember, first we want to just think about the data. Does this look like it's growing slow or growing fast? What do you guys think? Or growing at the same rate?
Slow.
When you go from 1 to 30 to 1,000 to 30,000, how much is Y changing by? Only 1 each time. So you might think constant like a line, but are these going up by the same amount? So it's not a line. Is it growing fast or slow though?
Slow.
Slow. Very, very slow. See, if you're just looking at these, you're not understanding what's happening here. What are we looking at to grow, X or Y? Y. You're always looking at to see what happens with Y usually. So Y is growing really, really, really slow. So what kind of function do you guys already think might be best for this before we even look at the graph? I think a logarithm. Logarithms have the slowest growth that we've seen so far. Later we'll look at square root functions and they kind of have a slow growth too, but those are the slow ones. Okay, so we haven't done one like this yet. Let's put it in our calculator, make sure you put it in there. Let's just see if it looks maybe like a logarithm, I don't know. So let's see, I'm going to turn this just slightly. Get rid of that calculus. Edit. So remember, I go up to the top. Anytime you want to do something to the whole list, like there's a lot of times we do this in later classes where we want to apply the same kind of operation to the entire list. You highlight it up here. So you'll see things like that later on, maybe even this year. We just got to put these in, right? 130,000 tons, 30,000 tons. Then we got 2, 3, 4, and 5 for the magnitudes of these explosions. So then you can go make sure your plot's on again. Remember, when we go back to function land and we stop doing this for a second, we'll come back and do this more this year for sure too. But remember, when you go back and forth between data and functions, you've got to turn these plots on and off, right? Or they'll get screwed up. So remember that you're going to have to be messing with that. Right now mine's on, so I'm good. I'm going to clear out what I have in y equals. And then I'm going to hit zoom. How do I get a nice scale for the window without messing with it by hand? If I have data, I go zoom. Stat, zoom 9. Down there. Okay. So I'm betting this is really big in the x direction, right? Because it goes from 1 to 30,000. If you want to actually see what it is, you can go to your window. And yeah, it looks like they made it fairly big on the x's. How big is it in the y's though? Pretty small. I'm going to maybe change that to 1 and 6 just to make it a little easier to read. Does it look like a logarithm? Yep. So I'm betting a logarithm is probably a good way to go. Does it look like a line? No way. Does it look like a U shape? Remember, a U shape could be right side up or transformed over. Does it look like this kind of a parabola shape though still? I don't think so. It's way too flat. It's got too slow of a growth. So no, we're going to do the logarithm. So go statistic. And now we're calculate a model. And we say we didn't want a line, we didn't want a quadratic parabola. We've never even used these two. Another line. That's natural log, right? ln. So there's our ln. Tell it your lists. Uh-oh. And there we go. So let's go explain r squared in context again. Remember, just besides looking at the picture, there's lots of ways to measure whether your model is good. We're just using two. Our two ways are to look at it and see if it looks right, kind of, which it did. And then also to look at your values for these coefficients. So r squared, is this a good value of r squared?
Yeah.
This is insanely good. Like in stats, when we do like real world data, almost all the time, it's really rare to get to this strong of an r squared. R squared like 0.8 would be really good. This is like insane. It's like almost perfect, yeah. It's almost really, really, really close to perfect. So let's say it in context though. So 99.996, insane. 99.996% of the variation in the y variable, which is what?
Magnitude.
In the magnitude of the explosion. I'm going to put magnitude of explosion, because otherwise I don't know what that means. Can be explained by variation in the tonnage of TNT. Okay, so remember, r squared tells you how much of the variation that you're seeing here can be explained by variation that's here using the model that you picked. If we go choose another model like quadratic, I bet it's going to be not nearly as good. We can go do it in a second if you guys want, maybe for one other thing. But now we got to write down the actual model, right? So y equals, notice they give you the form and the numbers to put in, so you put the numbers in. So y equals 2.003 plus 0.290 times the natural log of x. So is that just a plain logarithm? It's got transformations on it, right? What's this do? That shifts it up. But go back to our picture, remember? When you go back to your picture, does it look like that's been shifted up? Yeah, it looks like it's gone up to me. Remember, usually they go through like this. Does it look like it's been shifted up? Yes. And then what's this do to it? That's a vertical compression. Usually a logarithm looks like this one. Does it look flatter?
Yes.
It does look flatter, so that kind of makes sense that that's what's happening, yeah. If you want to actually see that, remember you can go put it in if you like. It's not really necessary, but if you want to put it in there, you can. Did they ask us for a prediction? I hope so. Use the model to estimate how many tons would make an earthquake above about 6.5. So which one of these things is the magnitude? I think the y is the magnitude, so we're going to put 6.5 here. Remember, they can ask you to use your model to predict y, or they can give you an x and ask you to, they can ask you to predict x or y, it depends. The model can be used for either thing. You just have to solve now. So you guys are going to need to help me. So if we're solving for x, what do I do?
Subtract 2.003.
So we get 4 point, somebody help me. Is that right? Yeah. Then what? You guys gonna let Megan do all the work? I'm not trying to do that in my head.
15.507.
And really the most important step is this. This is the only new step. You've known how to do that forever. Forever, forever, forever. How do I get x? How do I unlock it? That's a logarithm, use the exponential. So we get x is equal to e to the 15.507, which I'm betting this is a big number. Think about it. 6.5 is like over here, so it's got to be a much larger number. I'm betting like 50,000, 60,000. Oh.
5,427,558.722.
Thank you. What are the units? Tons of TNT. So if we're going to put that back in context like you guys need to on these problems, we'd say it would take about, remember this is just a predictions, it's not perfect, but it would take about 5 million tons of TNT to cause a magnitude 6.5 earthquake. So notice, when you're looking at earthquakes that are magnitude 2, it doesn't take much. You can make that, like man-made, you can make that kind of an earthquake pretty easily with 1 ton of TNT. But once you get down to like 5, it's not so easy. Yeah. Okay. Alright, I think that's good. So we shall stop there. Yeah, I have a worksheet.